All right, so now let's talk about that last point about how an XPS peak in the spectrum can be shifted due to its local environment or chemistry. So this could be viewed as a negative in that it's harder to know the exact position of an element's peak. But more importantly, this actually gives us unique information that other techniques can't. And so that's what XPS. So along with being surface sensitive, XPS and also AES give us this local environment of the element. And so not only do they give us the composition, they give us what's around it, and that's very important uh, to do with what chemical state it's in. And so we'll see some examples of this. So this is a chart we tend to see in some of the databases, and this is binding energies for an element, in this case carbon, and you can see the shifts with the different types of compounds. So a carbide, carbon bonded with nitrogen, carbon bonded with sulfur, all these will have different binding energies. And the total range is about 12 electron volts. So it's a pretty wide range. So again, that can make it harder to identify carbon, but it also could give us information about, is carbon bonded with nitrogen, is it bonded with oxygen, and so forth. And that can be useful to understanding the chemistry. And so we just saw that with the example of the polymer. A polymer, carbon tends to have multiple types of environments, and so we can make out multiple peaks corresponding to those multiple local environments. All right, so let's kind of look at why this occurs. And the first part I want to kind of bring up is shielding, right? So we know shielding as effectively that shielding of charge that an electron sees the nucleus by other closer electrons. And so there's more shielding between an electron. If there's more shielding between an electron and the nucleus, then the binding energy, which is what we're measuring, is lowered. Because if there's more shielding, it doesn't take as much energy to remove, for example, this electron if it's being, if basically the charge of the nucleus is being shielded, right? So it's harder, or it's easier to remove that. So basically, increased shielding lowers the binding energy. So that's one important thing to mention here. Obviously, shape and so forth matters as well. S versus P and so forth have different shapes, and so that will come into play. But typically, we're looking at core level electrons, and so the outer valence don't necessarily shield the nucleus as well. So all of that kind of is considered in this type of analysis. So the another kind of change that we can tend to see is a element's relative charge. So if we're in an ionic structure, for example, if it's an iron oxide or chloride, whatever it may be, we obviously will have different charges on the iron. And so if we have a positive charge, this means that there's fewer electrons in that ion. So trying to remove an additional electron becomes more difficult. So that means that that binding energy will decrease. That binding energy will increase. And so that's kind of what we see here. So this is the peak for iron 2+. This is for 3+, and we see it's shifted. In this case, again, binding energy increases to the left, so we have a higher number. Negative is basically the opposite. It means that we have more electrons, and so removing one becomes less difficult. So those will be shifted to decreasing binding energies. So charge has a big influence on this. Another thing, so if we're talking about charge, we're typically talking about ionic bonding, but covalent bonding can also affect the binding energy of a peak. So how much time an electron spins about around a relative element will therefore affect it. So in this example, carbon has a higher electronegativity, so it's effectively more negatively charged. It's more electron rich. And so basically in those cases, it's easier, therefore, to remove one electron because, again, this is, you can think of this as effectively negatively charged. And as we just saw, negatively charged decreases the binding energy. So same thing here. More electronegative elements will be decrease in binding energy. If we look at it from the opposite point of view, if we look at silicon in this silicon carbide, silicon has a lower electronegativity. And so therefore it's effectively positive charged. It's less electron rich, it's electron poor. And so it's harder to remove an electron from that element. And so it increases the binding energy. And so in that case, we see an increase in binding energy for silicon compounds. So the same thing. So covalent and ionic bonding will affect the binding energy. So all of this kind of goes into being able to determine the chemical environment, right? So in these previous, these peak locations tell us that we have that we have silicon, but it's bound to silicon is bound to carbon, or silicon is bound to oxygen. And so the peak position can then be used to backtrack and allow us to understand the local environment. And so that's what we can do here with metal surfaces. So as you are probably aware, aluminum metal, so that has a peak around, as you can see here, 76. But that's for the oxide. But aluminum metal tends to have a native oxide on it, on the surface. And so the aluminum peaks are over here closer to 73, but it does have an oxide shifted to higher binding energies because the aluminum would be positively charged. And so we see that around 76. And so so it allows us to understand we have both metallic form and an oxide form. So we can get that information. And then we can also, again, it's a surface sensitive technique. And so we can see here that they're saying the oxide layer is only about 4 nanometers. And so we're seeing a really strong oxide peak because it's a very surface sensitive technique. And so this is something, these kind of layers that we see, these very thin layers are often not even detected by XRD because they're either amorphous or too small. And so this is a good technique for determining the surface structure, whether it's oxide or clean or anything else. Even what we consider noble metals, so gold, platinum, things like that, tend to have some level of oxide on their surface. And so it's not a huge, obviously, layer, but it can be, a monolayer, a single layer or less, and that will show up. And so we can get that kind of information. So here we see PT0, so that means it's metallic, the charge is 0, but we also say PT2+, so it's an oxide or other form. And that's, again, shifted to higher binding energies by being shifted to the left in this graph. All right, so most of the stuff we've talked about so far has been, elements, a lot of metals and oxides, but XPS is very useful for polymers. It can be very useful for characterizing polymers as well, because like we had in the example before, carbon, which is the backbone of a lot of polymers, will tend to be in multiple forms with the different functional groups and the backbone and so forth. And so having those different chemical environments can be picked up and tied to a specific functional group using XPS. So a couple examples here: PET, polyethylene terephthalate, has multiple functional groups, and so you can kind of see the big peak here. You can see with the aromatic ring, and again, each one of them at a different binding energy tied to a specific group in the PET structure. So you can kind of see that up here. Same thing with polyvinyl chloride, different functional groups. There's obviously going to be some bound to chlorine, and so you're going to have different intensities, or sorry, different positions based on the relative binding energies. So, so this tells us information about carbon, and so for people who study carbon to a big extent, Raman spectroscopy tends to be very useful to determining the types of carbon we have. So you might be familiar with sp2, sp3. Those are very common forms of carbon that more or less ties back to the diamond structure and the graphite structure, so the different local environments. Well, we can get similar information in XPS as well. We can get differences in it. We can determine the relative amounts of sp2 and sp3 carbon, as you kind of see here. So the blue curve is diamond, which is pure sp3, and then sp2, which is the HOPG, which is highly oriented pyrolytic graphite. So basically pure graphite. And so we can kind of see those differences. And actually there's, again, one of those shake-up or satellite peak features that we see as well. So it allows us to determine amounts. And even if we have a mixed phase, we can get the different amounts in there as well. All right, so something else to kind of keep in mind for carbon, we saw that the range of binding energies for various compound types is about 12 eV. However, the shifts that we have, the magnitude tend to decrease with increasing atomic number. So if we go up to something like gold, the differences are a lot more subtle. So only 4 electron volts. So you see everything's very, very close together. So that can make things more difficult to visualize and determine the different types of compound types. And so a lot of times what we call peak deconvolution, so kind of fitting multiple peaks into one, that process has to be used in order to determine the different amounts. So kind of something like this. The one here, you can kind of see that if you just look at the peak itself, which is the black curve with the dots, you can see that it's not very symmetric. And so you can imagine that there's probably multiple peaks convoluted together, so just overlapped. And so the process of deconvolution is fitting such that we can kind of figure out what is going on in the one large just the not symmetric peak here. So the same thing, this is actually from some work that I did where, again, you can kind of see these peaks aren't symmetric. And so using fitting software like the CASA XPS or others, you can determine the different types in that. And so the peak shape tends to be Gaussian-Lorentzian. That's a common type that you can use in peak fitting software. And so that's the shape. And we also know the background, which again is that Shirley type with the step function. So both of those will allow us to do this deconvolution. All right, so let's go back to that first example I gave you with carbon. And I gave you these 4 peaks, 1, 2, 3, 4. And so if we're looking at that, I also gave you this compound type table with all the different binding energies. This is something that you'll see in databases that give you information. You'll have one of these in the a more complete, which has a lot of different elements and so forth. You'll have various versions of this on Canvas so that you can do the accompanying homework. But using the kind of information here and looking at these 4 peaks, see if you can go through and determine what possible types each one of those carbon bonds is. So pause the video, see if you can do that, use the figure here, and we'll come back and see if we can match those and see what the answer is. So pause it, come back, and we will discuss. All right, so now that you've had a chance to look at this, let's see what you got. So I tried to overlay the peak positions from the previous page onto that plot for you and to kind of see what types of bonds that we can have. So for the first one, the lowest, we see that it could be carbon. And then it's, kind of right on the edge there of maybe the carbon with nitrogen. the next one, as you see, that there's a lot of different things that could potentially be. So we'll come back to that one. This next one definitely could be this carbonate or CHF, and then maybe on the brink there of carbon chlorine. And then this last one seems to be this carbon with fluorine. So let's see what it actually is. This plot, there's a little bit different numbers here, so kind of ignore the numbers, but the numbers, the actual peaks are the same. And so we see that the lowest peak, which is 1 over here, they are again calling this the carbon-carbon backbone. So that's great. So it's pretty close to what we see here. The second one, you can see that we have this carbon-oxygen, and so it looks like it's one of these functional groups here that, in this middle cluster. The next one is 3 down here. So again, it's another one of those carbon oxygen. And then the last one we see is the CF3, which corresponds to the position down here. So obviously, you're dealing with a kind of range here. So oftentimes you'll find more specific values in database like this, but these just give you some ideas. And you can see that if our calibration isn't correct, if our position for carbon wasn't correct, then everything else would obviously be shifted. And so that's important to make sure we have the proper calibration. So obviously I wasn't expecting too much for this middle one where you've got a lot of different options. So along with this, as you can imagine, you're not going to be able to just say which one of these is purely by the number, because there's a lot of different options. So if you think it's carbon with nitrogen, you would also want to run the scan to see if there's actually nitrogen. Same thing with sulfur. So that would give you a lot of information. So you can kind of look up here and see that it's carbon, oxygen, fluorine, hydrogen. So if your scan didn't pick up those things, so we're probably not looking at nitrogen, sulfur, definitely oxygen, and then fluorine. So that you also have to use other pieces of information to be able to really accurately determine what these peaks correspond to. And then this is just a different type of the same thing, just kind of showing you different effects to do with the bond enthalpy. And this kind of shows you some of those effects of shielding and charge and the different peak shifts that we see. So we see that the carbon-fluorine bond is very strong and has that's 4. So it has the highest binding energy. So it's harder to remove a carbon electron from a carbon here than it is from the carbon-carbon because of that much stronger bond. So this is just another way of looking at that same plot. All right, so let me briefly talk about AES. So, and the good thing to know about AES when it comes to the local environments is that the shifts, these chemical shifts that affect the peak location tend to be larger. And also, they can actually change the shape. So if we look at some various forms down here, so these are all oxides that we see. So we're looking at oxygen, and you can see that obviously there's a change in the peak location on the x-axis, but also there's a very different peak shape in all of these. And so this is that oxygen KLL-OJ peak for various oxides. So we see peaks vary about 5 electron volts, and then there can also vary in shape depending on what the local environment is. So we won't talk as much about AES in terms of these peak shifts, but just keep in mind that it can be quite large and affect the peak shape as well.